Thank you very much for watching this video. I also appreciate your interest in learning more about the project. My name is Adolfo Perez, and with my colleague and advisor, Dr. Cristian Dominguez, we developed this project named The Role of Tropical Cyclone Size in Precipitation over Mexico. This presentation is part of the EGU General Assembly 2022. So, to explain a little more about what we did, we have divided this presentation into four sections. The first part tells the story by explaining why we did this project, followed by a summary overview of our methodology, continuing with a summary of our results and discussions, to end with the conclusions of the project and their application in tools to mitigate the danger of tropical cyclones early warning systems. Mexico, as well as other regions belonging to Central America, year after year see the presence of tropical cyclones, both in the Atlantic region in red dots and in the Eastern Pacific region in gray dots in the figure 1. These systems, besides being a water resource to avoid droughts, are an important risk due to the high vulnerability of these regions. The tropical cyclone hazard may be due to strong winds, storm surge, and torrential rainfall impacts in the region near to the center of the storm. However, because this system can grow, some rainband not so close to the center may remain in regions and cause severe flooding or landslide. Therefore, not only regions directly affected by tropical cyclones should not be the only ones of concern to disaster prevention agencies. But then, what happens in the region when the tropical cyclone hazard exists? In Mexico, we have an early warning system for tropical cyclones that uses a color scale to communicate to the populations and decision makers in order to propose risk mitigation strategies. But there are two important details in the definition of dangers of tropical cyclone. First, the early warning system uses a very small measure of size that is defined as a radius from the center of the storm to where 34 knots of wind speed is reached. Secondly, its danger scale gives a greater weight to tropical cyclones that have a hurricane category. In spite of this, several studies have shown that the category is not related to the amount of precipitation, and the damage in the region is mainly due to the precipitation. In addition, the storms that most directly affect Mexico are usually of lower categories, as we can see in the figure 2. This is why improving emergency management for tropical cyclone associated risk is urgent. Therefore, the main objective of this project is to define the size of tropical cyclones that affect Mexico during the period of 2000 and 2020 by using infrared satellite imagery. Defining a new size of tropical cyclones will be an appropriate response to make the early warning system more accurate in defining the hazard. Keeping this in consideration, these databases were selected to continue with the main objective of the project. The trajectory information of the tropical cyclones was taken from the URDA 2 of the NOAA, with positions in latitude and longitude for each position every 6 hours. To delimit the area, we use the size of the tropical cyclone wind field. A database made by Perez Alarcón and collaborators is used, which uses the wind profile described by Willoughby and collaborator with information of the minimum pressure at sea level and the size of the maximum wind radius. With this, it is possible to estimate with the operational information. Therefore, it fulfills the objectives of the project. The areas of possible precipitation are estimated using infrared satellite products called GPM merging. For more information on these databases, you can follow the QR code next to them on the slide. For other parts of the methodology, precipitation data are used from GPM products and CHIPS data, as well as values of environmental variables such as humidity, wind speed, and vertical velocity from the ERAFI reanalysis database. So to measure this size, considering the rainfall, we use the input data. tropical cyclone position, infrared image of the momentum reported by URDAT, and the size of wind field. These go into the algorithm we create called ROCLA. The first step in this algorithm is to segment the infrared image at a threshold of minus 40 degrees, which we designate as possible regions of interest for precipitation, or ROIs. These are shown in gray in the figure 3. These ROIs are converted to georeferenced polygons to work in an automated geographic information system, or Python HIS. However, as the image considers even areas beyond the storm region and differentiate them from other possible phenomena, only the polygons that intersect the area of the wind field defined by the input size are taken into account. The contours of the polygons are converted into points to measure the distance from the center of the storm to each of them and take only the maximum value for each quadrant defined as northeast, northwest, southwest, and southeast, as shown in the figure 3. So for radii per position is calculated. Finally, an average affected area is calculated using the information of the 4 radii previously obtained. Our results are presented first as a climatology considering from 2000 to 2020 for tropical cyclones within the study area, being 191 cyclones in the Atlantic and 337 cyclones in the Pacific. In the figure 4, we can observe that the tropical cyclones present average size between 200 and 1,500 kilometers for both basins, being the Atlantic that the one that presents greater sizes. Regarding the importance of the radii per quadrant, we observe that in both basins it is the northeast radius that presents the larger size, being this the one with the most precipitation. But it is really possible to affirm this. Therefore, the results are grouped in 3 sections. Number 1, how much does the intensity and position of the tropical cyclone influence the hazard? Number 2, is the selected threshold hypothesis adequate to represent precipitation? And number 3, how to explain the amount of precipitation as a function of the calculated size. The first question highlights the following important points. Considering the average distribution of the tropical cyclones radii as shown in the figure 5, we observe first of all how in most cases when they are contact with the warmer waters belonging to the warm water pool areas, transitions to extratropical environments, and when they approach to the continental coast. The reasons are based on the dynamics of the tropical cyclones that work with the moisture fluxes coming from warm oceans, and that when there is a friction with the continental regions, a loss of intensity deploys a lesser organization of cumulus clusters, extending to the regions far from the center, to which our size calculations are sensitive. Following the theory that a tropical cyclone's transition from a maximum intensity to a decreasing intensity over the time could explain a larger size, we calculated the average behavior as soon as they reach their maximum intensity. The plot shows precisely how there is no visible sign of such behavior provided with the defined size information. Even the Pacific shows a decrease after reaching the maximum intensity. Finally, considering only the size, we can observe that the cyclonic season in the region from May to November, we can see how they occur more frequently in August in both basins, represented by the lines in the figure 7. Furthermore, if we define the tropical cyclones by size as small or large, depending on the lower and upper quartile, we can see that September is when the most large tropical cyclones occur in both basins, which will be the month with the greatest impacts. The second part of the results are focused on the relation of the calculated size to describe the precipitation in the presence of a tropical cyclone. For this purpose, two different approaches are used. From the first point, we consider a similar methodology that proposed with raw cloud, but now we using precipitation products and measuring the radii to where the 2.5 millimeters rainfall polygons are located. Considering this, the climatology of precipitation sizes shows similar sizes to those observed in rock cloud, as shown in the figure 8. Besides that, just in the Atlantic, they tend to be larger than in the Pacific. Having both databases with the proposed sizes, with infrared imagery, and with the satellite precipitation products from the GPM, a comparison is obtained by calculating correlations to know how the small and large sizes of the rock cloud respond to the precipitation sizes. As seen in this slide, a strong positive Spearman correlation is observed between both databases in all radis. This allows to apparently relate that the first, the select threshold, functioned as an indicator of rainfall regions, and therefore the sizes calculated with rock cloud appropriately describe the areas with the precipitation affectations in our study area. The second point seeks to analyze specifically where we can expect rain in the storms that enter the study using radial precipitation profiles. According to the positions every 6 hours and with the GPM products information, we can observe a notorious range in a rainfall range is observed with greater intensity up to 500 kilometers, although it is possible to visualize the presence of precipitations up to 750 kilometers. Although it is possible to see how precipitations behave in the continental regions in the figure 10, because the satellite precipitations products have shown biases in their values over the continental regions, a similar approach to the profiles with GPN, but now with CHIRPS data, is used to see how the daily precipitations behaves in continental regions. The figure 12 shows that even ranges beyond even 150 kilometers from the center report significant daily precipitation rates in both basins. Therefore, the proposed size could indicate to us by having sizes that consider these regions adequate to define the appropriate regions of danger. The last part of our analysis brings to the table how the environmental variables involved in the tropical cyclones environment influence the prediction of precipitation. Using a methodology that utilizes correlational analysis and generalized estimating equations model, we obtain the following results. Some tropical cyclones show strong divergence in the upper atmosphere. It may be related to large amounts of the moisture in the mid-level atmosphere, producing intense tropical cyclones at the surface. Tropical cyclones in dry environments produce less precipitation and have a smaller radial wind station when compared to tropical cyclones in moist environments. Wind shear is more important for tropical cyclones over the Atlantic basin. The latter is possible related to the fact that tropical cyclones' trajectories near the landmass are modified by environmental shear. And finally, neither tropical cyclone nor sea level pressure are important for the estimation of tropical cyclone rainfall related with the inside of the outer tropical cyclone size. Finally, our conclusions in responses to the questions posed above lead us to consider the following results. First, how much the tropical cyclone's intensity and positions influence the hazard. The sizes calculated by rock cloud are comparable with those of other studies, but adding the importance of precipitation in the area. And making a proper analysis of the role of size with intensity is that the Saffir-Simpson scale by itself does not indicate how big a tropical cyclone can be. It should be clarified that its size does not imply the shape of the storm. Second, is the select threshold hypothesis adequate to represent precipitation? The select threshold and the size itself are functional for identifying regions of the cyclone where there is a potential precipitation, as well as encompassing regions that radial profiles indicate significant rainfall rates, which are approximately 750 kilometers. And finally, how to account for the amount of precipitation as a function of the calculated size. The environmental variables should also be considered to perform a more appropriate analysis of the amount of precipitation and their calculation with the environment enclosed by the proposed size. But how do our results work in a real world context? The case of 2020 tropical cyclone Cristobal over southeastern Mexico is a recent example of the underestimation that the early warning system can have with lower intensity tropical cyclones. This tropical storm was leaving major disaster in vulnerable regions of Yucatan. The black squares marked as 1, 2, 3 are the ones that reported the highest precipitation according to CHIRP's data on June 4th. We will focus on them to analyze how the warnings were underestimated. This work modifies the alerts every 6 hours, changing the circulation value factor of the tropical cyclone, changing the R34 to the size calculated with the raw cloud in this project. Blue and green colors are issued for minimum danger, yellow for moderate danger, and orange or red for high danger. In the figure 12, on the left, we can find the alerts issued by the early warning system, and on the right, proposed with the slight changes in this project. The first two warnings issued on June 4th marked regions as minimum danger since the category of the system was tropical storm, but a slight improvement in the sizing of the warnings begins to be seen, replacing by the size that considers precipitation, extending areas of moderate rain danger. Nonetheless, in the following days, the system was downgraded to a tropical depression, which implied a loss of its danger scale value in the early warning system. These were critical hours since it was partial seasonality due to the low translation speed, which causes the precipitation's amount to increase. We note on the left that our selected regions fluctuate between minimum to moderate hazard, while the modification of the circulation scale market areas fluctuate between moderate and high hazard in the regions of interest. This brings to the table that appropriate changes need to be made that give weight to both the circulation scale and the intensity scale. This will be part of the future work of this project. So, in the meantime, we thank you for your interest in learning more about our project. If you still have any doubts or comments, we hope you will write to us at the email addresses shown on the screen. So, thank you very much and have a nice day ahead.